You have probably watched a burger patty turn brown in a pan. That color is iron losing one electron to oxygen. Mars did the same thing, and that is not an analogy. Most people assume Mars was always red. It was not. The red took 4 billion years. Same electron transfer. The only difference was temperature. The bright red of beef in a butcher's display is one of those colors that seems to mean something. Most people read it as freshness, as the visible signal that the meat is exactly what it should be. And the assumption behind that reading is reasonable enough. The color is vivid, specific, almost confident. It announces itself. But that color is not what beef looks like when it is resting. It is what iron looks like when it is actively holding an oxygen molecule. The bright red of the open display case is not a passive property of the meat. It is the consequence of a protein doing something, specifically a protein called myoglobin and the iron atom at its center, engaged in the act of binding and holding oxygen inside the muscle tissue. The moment the iron releases that oxygen, or the moment oxygen is removed from the surrounding environment, the color changes, and it changes to something most people would not expect to see. The color underneath, the one that appears when oxygen is not in the picture, is a deep purple red, closer to dark wine than to the vivid red of the display, a color most people associate with something gone wrong. I remember the day I got properly ready at home and headed to the supermarket to pick up some beef. I will admit I have never been particularly enthusiastic about grocery shopping, though there are times when you simply have no choice. The butchered cuts you find in a supermarket are vacuum sealed to extend their shelf life, every trace of air removed from the packaging, and the color was so deeply purple red that the moment you look at it, you cannot help but ask, what on earth is that? Watch what I did. I picked up one package, turned it over, checked the date, put it back, reached for another, same color, then a third, same again. I left without buying anything. There is always something faintly strange about walking out of a supermarket empty-handed, and my inner voice was practically narrating the whole thing. Just leave calmly, you are not a thief, you came, you looked, it was not what you wanted, you are walking out like a perfectly normal person, nobody is going to say a word. Looking back, I can say that was not exactly rational behavior. I found out later that what I had been looking at was simply the same iron atom in a different chemical state. The beef was not spoiled, it was just chemistry. That purple red has a name. It's called deoxymyoglobin. The form myoglobin cakes when the iron is in its Fe2+ state, which is to say when it has lost 2 electrons from its neutral condition, but no oxygen molecule is attached to it. The protein is complete, the iron is present, the geometry of the molecule is intact, but there is nothing bound to the iron right now, and without that binding, the way the molecule interacts with visible light shifts just enough to produce a different color. The iron is waiting, in other words. The purple red is what waiting looks like. The bright red is different. It is called oxymyoglobin, the form that appears when the Fe2+ iron has picked up one oxygen molecule and is actively holding it. When oxygen binds to the iron, the geometry of the protein shifts slightly. The distances between specific atoms change by fractions of a nanometer. And that fractional shift alters how the heme group, The iron-containing structure at the protein's center absorbs and reflects light. The vivid red is not an accident of composition. It is the consequence of the iron in the act of holding something. And here is the question that follows naturally from that. What is the iron holding oxygen for? Myoglobin's job is to store oxygen inside muscle cells between heartbeats. Hemoglobin, the protein in red blood cells, carries oxygen through the bloodstream and releases it as blood flows through the capillaries. But hemoglobin cannot cross into the muscle cell itself. What crosses is the oxygen it releases, and that oxygen is picked up immediately by myoglobin on the other side, held there until the muscle contracts and burns it. One heartbeat supplies, the next moment burns. Between those two events, myoglobin holds. There is something in this that does not have a tidy name in the scientific literature. The kind of effort that is invisible because it never fails. It announces nothing to anyone. It holds the oxygen it needs to hold, and because it does, the system that depends on it can carry on without interruption. The purple red and the bright red are both expressions of the same duty, one actively holding, the other ready to hold. The iron here reminds me of a friend of mine at the office, the one doing the most essential work in the building, somehow ending up with the smallest paycheck. The protein itself is not large, though it is precisely made. 153 amino acids folded through a series of 8 helical sections that wrap around a central structure, like a carefully arranged piece of origami around a single point. And at the geometric center of everything, at the exact middle of the fold, sits one heme group. Let me slow down here because this structure is worth it. It is a flat ring called a porphyrin ring, and the iron atom sits at its exact geometric center, held by 4 nitrogen atoms arranged symmetrically around it, each one bonded to the iron simultaneously, not roughly in the middle, at the exact center, a position defined by the symmetry of the ring itself, maintained by the equal pull of 4 bonds at 90 degrees to each other. When you hold a raw piece of beef, the weight of it in your palm, the slight chill from the refrigerator cabinet, the faint smell that is closer to iron filings than to anything else, that geometry is inside it. Every gram. I have held a piece of beef with that thought in mind and found the ordinary weight of it changes slightly. Not the beef, the thought. What I found genuinely arresting when I first looked into this is that this same basic arrangement, one iron atom inside a porphyrin ring, appears in very nearly every oxygen-using organism on Earth. Insects, fish, every mammal. The chemistry that makes myoglobin function was solved very early in the history of complex life and has been maintained almost without modification ever since. The heme group is not a recent development. It is one of the oldest functional structures in biology. That a configuration precise enough to hold a single oxygen molecule in a controlled binding state has been kept essentially unchanged across this range of life, that, I have to say, is not something I had expected to find when I started reading about why a burger turns brown. This is an analogy that is not quite perfect, and I want to say so directly. Thinking of the heme group as a lock and the oxygen molecule as a key gets you part way there. The binding is specific, the geometry matters, the fit is not accidental. But a lock is passive. The iron in myoglobin is not passive. The binding involves actual electron interactions. The iron's Fe2+ state is what makes binding possible, and a change in that state is what ends it. The lock and key image helps, and then it stops helping. The more accurate picture is that the iron is an active participant in the holding. And here is something the science does not yet fully explain, which I think is worth saying plainly. Why the same heme configuration persists across animals as different as an insect and a sperm whale. The binding geometry is conserved. The oxidation state is conserved. But the evolutionary reasons this particular solution stayed unchanged across hundreds of millions of years are not completely resolved. The chemistry is stable. The explanation for why it persisted is still being argued over. A further question follows. What happens when the same iron chemistry scales up from a small land animal to something that dives 600 meters? Myoglobin concentration varies considerably from one muscle to another, and that variation explains something most people have noticed without asking why. The dark leg meat of a chicken contains far more myoglobin than the pale breast meat. Leg muscles work continuously, and the oxygen demand is sustained. Breast muscles are used in short bursts. The concentration is proportional to the sustained oxygen demand. More working muscle needs more myoglobin, and more myoglobin produces a deeper color. This is not a species-specific quirk. It is a principle that holds across animal classes. Deep-diving marine mammals take this further. The myoglobin concentration in the muscle of a sperm whale is several times higher than in a typical land mammal, producing tissue that is near black in color. The whale's muscle does not simply store oxygen between heartbeats. It stores enough oxygen to sustain a dive of 90 minutes without breathing. The iron atom in that tissue is doing the same job as the iron in beef myoglobin. The chemistry is identical. The scale and duration are not. So there are, at this point in the story, two states to hold in mind. The Fe2+ iron in myoglobin produces either purple-red or bright red, depending on whether oxygen is attached. Both of these are the iron at rest in its characteristic state. And then there is a third color, the one that requires something from outside the system. Not the absence of oxygen, the presence of heat. Above a certain temperature threshold, the iron atom in myoglobin does not simply release its oxygen and return to the purple-red of deoxymyoglobin. Something more fundamental happens. The iron loses one additional electron. Fe2+ becomes Fe3+. The protein changes permanently. The color produced is brown, specifically the brown-gray of cooked meat, which has its own name, metmyoglobin. And this shift from Fe2+ to Fe3+ is not just a change in a cooking property. It is one instance of a chemical reaction that operates at every scale at which iron and oxygen exist under the right conditions, from the inside of a muscle protein to the surface of a planet. The next chapter is about what that electron transfer actually is, because before Mars enters this story, the chemistry itself needs to be completely clear. And the chemistry, once it is understood properly, turns out to be something most people have been watching their whole life without realizing it had a name. The outside of the patty goes brown. The inside stays pink for a while. The whole thing eventually turns gray-brown all the way through, and we say the burger is done. This sequence is so familiar it stops being interesting. It is just what cooking looks like. But the browning of meat, the specific color change that turns an iron-containing protein from red to brown, is not simply cooking in the everyday sense. It is electrochemistry. It is, in a precise and measurable way, the same process as rusting. And understanding why that is true requires going to the level of the electron. Suppose you have a nail left outdoors after a rainstorm. Within a day or two, the surface begins to show a faint orange tinge. Within a week, that orange has deepened. Within a month, depending on conditions, the surface is visibly changed. The smooth gray silver has been replaced by a rough, reddish-brown crust that flakes when pressed. Most people know this process as rusting. Fewer have asked what is actually happening at the atomic level to produce it. What is happening is this. The iron atoms at the surface of the nail are losing electrons to oxygen in the surrounding air and moisture. An iron atom in its neutral state has 26 electrons. In elemental metal, iron exists in the Fe0 state, all electrons present. But at the nail's surface, where iron meets the thin film of water left by rain, iron atoms begin releasing electrons and dissolving as Fe2+, the same oxidation state as the iron in myoglobin. In the presence of oxygen, that Fe2+ loses one more electron. It becomes Fe3+. And the iron oxide compounds that form when Fe3+ combines with oxygen, compounds like hematite, like goethite, are the specific molecules that produce the red and orange-brown colors associated with rust. This is oxidation, not in the casual sense of the word, not simply exposure to air. In the precise chemical definition, oxidation means one thing only. A substance loses electrons to another substance. Iron loses an electron. Oxygen gains it. That transfer is the reaction, and the color change from the silvery gray of elemental iron to the orange-red of iron oxide is the visible consequence of what happened at the electron level. There is something easy to miss about what water is doing in the rusting process. Easy to miss because water looks exactly like a bystander, something that gets the nail wet without being part of the chemistry itself. And that reading is entirely understandable. Water is transparent. It sits there, passive-seeming, and seems to contribute nothing beyond getting the surface damp. Except that reading is wrong. Water does not witness the electron transfer, it enables it. Acting as the conductive medium across the metal's surface, it dissolves trace ions and provides the pathway through which iron and oxygen can actually exchange electrons at any useful rate. Remove the water, and the rusting slows to almost nothing. A nail left in genuinely dry air barely changes. Bring the water back, and the same iron begins to react within days. Water is not present for the rust. Water is the reason the rust can proceed. I once left a short steel rod on a window ledge, and it just stayed there. I can't remember the exact details. I was doing some work, and once I finished, I was probably happy enough about that to walk off and forget the rod entirely. About 3 weeks later, my sister called out to me in the yard. I leaned out the window to look at her, and that is when I saw the rod still sitting there, and saw that the side facing the rain had turned a full, even orange. The underside, which had stayed mostly dry, had barely changed at all, I can tell you. The chemistry was equally available to both faces, so if you ask what was the difference was the water. There is something in that observation worth naming. The nail does not decide to rust. It simply changes when the conditions that permit the change arrive. And once those conditions have done their work, the result is not something that lightly undoes itself. An electron transferred is an electron that does not return on its own. Some changes reveal their permanence not in the moment of happening, which can look like a slow recoloring, an unhurried surface becoming, but only afterwards, when you look at what is left and realize the thing cannot go back. Iron rusting on a gatepost has that quality. It will not spontaneously return to gray silver. The direction is set. What the water enabled stays enabled. A question follows from this. How does a 4-minute kitchen event and a geological process that takes billions of years turn out to be the same chemistry? The Fe2+ iron at the center of the myoglobin heme group loses 1 electron to oxygen when temperature is applied. Fe2+ becomes Fe3+. A new form of myoglobin is produced, metmyoglobin, that is brown. The color change from the pink red of raw beef to the brown of cooked beef is chemically identical to the color change from the gray of a new nail to the orange red of a rusted one. In both cases, Fe2+ lost 1 electron to oxygen. In both cases, Fe3+ produced a visually distinct iron compound. In both cases, the change is essentially irreversible under normal conditions. I want to tell you something about this parallel. The thing is, cooking a burger and rusting a nail truly do involve the same electron transfer, but we cannot say they are completely identical things because they are not. Temperature, time scale, protein environment, all of these are different. The analogy holds at the level of the iron atom. The moment you step beyond that, it falls apart. It is useful, but only if you know where its limits are. The word essentially is doing some work in that irreversibility claim, and I want to be precise about it. There are conditions under which myoglobin can be partially reduced back. Certain reducing agents can return Fe3+ metmyoglobin toward Fe2+ forms. In industrial meat processing, these pathways are studied carefully because the browning of meat during storage is an economic problem as much as a chemical one. But under normal cooking conditions, the formation of metmyoglobin above the relevant temperature threshold is irreversible. The iron has changed state. The protein has changed state. The color is the record of both. What drives the reaction is temperature. Heat increases the kinetic energy of every molecule in the system. the myoglobin protein, the surrounding water, the oxygen molecules present within the tissue. As that energy increases, the rate of the electron transfer between Fe2+ and oxygen increases correspondingly. Below a certain threshold, the reaction happens slowly, if at all. Above it, the reaction becomes rapid enough to produce visible color change in minutes rather than hours. The specific threshold where met-myoglobin formation becomes rapid in ground beef is approximately 60 degrees Celsius. Below 50 degrees, oxymyoglobin remains the dominant form. The meat stays pink to red. In the range between 60 and 70 degrees, met-myoglobin forms quickly. This is where the color shift from red to brown occurs most visibly during cooking. Above 80 degrees, the myoglobin protein itself begins to fully denature. The protein's folded structure unravels, the heme group loses its organized environment, and the result is the gray-brown of an overcooked patty. The iron is still in the Fe3+ state, but the protein cage around it has collapsed. Is all of the browning during cooking caused by myoglobin oxidation? No. The Maillard reaction, a separate set of chemical reactions between amino acids and sugars at the meat's surface, also contributes significantly to the color and flavor of a cooked patty. At the surface of the meat, where temperatures can exceed 150 degrees Celsius during pan cooking, the Maillard reaction is responsible for a large portion of what is seen and smelled. The browned crust of a well-seared burger is not simply met-myoglobin, it is a mixture of met-myoglobin formation in the muscle proteins and Maillard products from the surface reactions. Inside the meat, however, where temperatures stay lower and surface chemistry does not apply, myoglobin oxidation is the primary driver of the color change. The brown interior of a cooked patty is predominantly met-myoglobin. The Maillard reaction also deserves a brief clarification in its own right, because the two processes are sometimes confused. It is not oxidation in the electrochemical sense. It does not involve iron losing an electron to oxygen. It is a condensation reaction. Amino groups from amino acids react with carbonyl groups from sugars to form hundreds of volatile and colored compounds. The flavor, the smell that rises from the pan, the character of the browned crust, those are Maillard products. The gray-brown of the interior is met-myoglobin. Two separate processes, two separate color contributions, running simultaneously in the same piece of meat at different temperatures through different chemistry. The smell is one story, the color inside is another. When oxidation is complete, iron seems to put on a new set of clothes and no longer resembles itself. The orange rust covers the silver gray of the metal entirely, as if blocking the original color from ever showing through again. This quality, permanent, one-way change, exists whether the iron is inside a protein cooked in 4 minutes or inside a mineral deposited over 4 billion years. The scale changes by a factor that is almost incomprehensible, but the direction never changes. I want to be honest about a gap in the science here, because it is a real one. The precise molecular pathway by which myoglobin oxidizes during cooking, the intermediate states between the Fe2+ form and the final Fe3+ met-myoglobin, is not fully characterized. The starting point is known, the end point is known, The overall reaction is well established, but the intermediate steps, the exact order in which the protein structure responds to heat and the electronic changes propagate through the heme group, are still studied and not completely resolved. The irreversibility of the Fe2+ to Fe3+ shift is worth staying with for a moment, not as a philosophical point, but as a purely physical one. Returning the iron to the Fe2+ state under cooking conditions would require introducing a specific reducing agent. The direction of the reaction is not neutral. Electron transfers have a natural direction, driven by the relative affinities of the atoms involved. Iron, in the presence of oxygen at elevated temperatures, releases electrons. Oxygen takes them. This is not a tendency, it is a description of what happens when those conditions are met. And this specific quality of a directed, irreversible electron transfer between iron and oxygen is what connects a 4-minute cooking event to a geological timescale. Because this same transfer, running on a planetary surface across billions of years, produced the color that makes Mars identifiable from Earth with the naked eye. But before that chapter opens, there is one more thing the burger has to show. The brown of a cooked patty is not a single uniform state. It passes through color changes in a specific order at specific temperatures, driven by a specific sequence of chemical events. And the story of those transitions, told in temperature thresholds and iron states, is cleaner and more instructive than it might first appear. That is the next chapter, and it turns out that the color record of a cooking burger, read properly, is a more informative document than most people would expect from something that takes 4 minutes. A burger cooking in a pan goes through 3 distinct color states, and if you watch it closely enough, the timing of those changes is not random. The shifts happen at specific temperatures driven by specific chemical events, and each color is a direct reading of the iron atom's current state. Most people watch this sequence happen dozens or hundreds of times across a lifetime without reading it as the chemical record it is. The first state is the one the raw patty begins in. At room temperature and across the lower range of cooking temperatures, roughly below 50 degrees Celsius, oxymyoglobin remains the dominant form. The outer surface of the patty, where oxygen from the air is in direct contact with the tissue, is bright red. The interior, where oxygen diffusion is more common, is slightly darker, more purple-red. As heat begins to penetrate the meat, this arrangement persists for a while. The outer surface warms first, but the chemistry of the iron has not yet reached the threshold for rapid oxidation. The patty still reads, in color terms, as raw. The shift begins at around 60 degrees Celsius. Above this threshold, metmyoglobin formation accelerates significantly. The Fe2+ begins losing its electron to oxygen at a rate fast enough to produce visible browning in minutes. The surface of the patty, which reaches this temperature first, being in direct contact with the pan, begins to transition from red to a gray-brown. This is metmyoglobin, the Fe3+ form of the protein, brown because the iron's new oxidation state shifts the heme group's light absorption in a way that eliminates the red contribution and leaves only the gray-brown. The surface is, in the chemical sense, completing its rust, a thin layer at a time. The interior lags because temperature lags. The surface of a patty in a 200-degree pan may reach browning temperature within the first minute. The center, depending on the thickness of the patty, may not reach 60 degrees for 3 or 4 minutes or more. This is why a well-seared burger can be brown on the outside and visibly pink in the middle. It is not a sign of incomplete cooking in a chemical sense. The interior iron simply has not yet reached the temperature at which the Fe2+ to Fe3+ transition becomes rapid. The pink interior is still mostly oxymyoglobin or deoxymyoglobin. The iron there is still in its Fe2+ state. It is not that the interior has refused to change. It is that the conditions for change have not yet arrived. I was standing near the ceiling, watching what was happening here. While cooking the patty, the brown color was advancing from the edge inward. The center of the patty, as normal, remained pink. Even though I couldn't fully explain this in words, I witnessed the chemical boundary moving in real time. There wasn't just a heat front there was also an oxidation front. The line between Fe2+ and Fe3+ iron ions advancing as the temperature rose. I saw the boundary run and observed it being absorbed in a strange way. Honestly, I went into this topic assuming I understood the pink interior of a burger. I assumed it was simply a matter of heat not penetrating far enough, and that the color would change the moment temperature did. What I had not thought about carefully is that the color and the temperature are measuring two different things. The pink is not raw in a simple sense. It is the iron in a specific oxidation state, and that state changes when and only when the relevant temperature threshold is crossed. The temperature determines when the chemistry occurs. The color records that the chemistry has occurred or has not. They are the same thing described at different levels, and I had been collapsing them into one idea when they are actually two. This is an analogy that has limits I want to name. Treating color as a direct temperature reading is useful, but imprecise, because color tracks iron state, which is affected not just by temperature, but by oxygen availability, myoglobin concentration, and the pH of the meat. The color is a downstream signal, useful, not the same as a thermometer. Does the color of a burger tell you whether it is safe to eat? Here is where most people's intuition leads them wrong. The color says one thing, the food safety threshold says another, and they do not speak to each other at all. The standard food safety threshold for ground beef, 71 degrees Celsius, as specified by the USDA, is a bacterial threshold. It is the internal temperature at which the relevant pathogens have been heat inactivated to a sufficient degree. It has nothing to do with the color of the meat. You might expect, given how closely the browning and the cooking seem to arrive together in everyday experience, that a fully browned burger is a safely cooked one. That assumption is false in both directions. A burger can reach 71 internally while still showing pink in some areas, depending on the myoglobin concentration and the pH of the meat. A burger can turn fully brown before reaching 71 degrees internally, depending on other conditions. The color and the bacterial safety threshold are chemically unrelated, They run in parallel, driven by different processes, arriving close enough together most of the time that the coincidence looks like a rule. The times they diverge are the ones that matter. A thermometer, not a color, is the only reliable report. The myoglobin concentration of the meat is one reason color is an unreliable guide to doneness. A patty made from beef with naturally high myoglobin content, older animals, heavily worked muscles, will retain pink tones at higher internal temperatures than a patty made from lower myoglobin cuts. The iron is there in greater quantity, and more of it needs to transition to Fe3+ before the visual change becomes uniform. Conversely, a patty with lower myoglobin content can appear fully brown at an internal temperature that has not yet reached the bacterial safety threshold. These are not edge cases. They are the normal variation across the kinds of beef sold in a typical supermarket. The meat's color is responding to its own iron chemistry. It is not responding to the bacteria. Those are two entirely separate processes happening in the same patty at the same time, and they do not coordinate with each other. When we cook something, we think the bacteria inside it die as soon as it cooks, but in reality, the cooking process and the death of the bacteria inside the food happen at separate times. The cook assumes these happen at the same moment, because in most cases they do happen at the same time. This assumption appears consistent. The cases where they diverge, though, are the most important ones. Before we continue with the video, I have a quick request. If you enjoy this type of video, liking it and subscribing to Sleepy Alchemy really helps others who need this kind of content find it. Above 80 degrees Celsius, a third state becomes visible. At this temperature, the myoglobin protein itself begins to fully denature. The folded structure of 153 amino acids, maintained by the precise geometry of those 8 helical sections, begins to unravel. The protein loses its organized shape. The heme group, which previously sat at the center of an intact fold, now sits in a collapsed, denatured protein chain. The iron remains in the Fe3+ state. The color remains brown-gray, but the texture of the meat changes noticeably at this threshold. The proteins of the muscle fiber are contracting and toughening. Water is being expelled. The familiar dry, firm texture of an overcooked patty is beginning to form. This gray-brown is denatured metmyoglobin. The chemistry of the iron is complete. The architecture that housed it has changed. The smell of a cooking burger at different stages corresponds, loosely, imperfectly, to the chemical stages. In the early phase, below 60 degrees, the smell is primarily of warming fat and liquid releasing from the tissue. The Maillard products have not yet formed in quantity on the surface. As the surface temperature climbs past 120 degrees and the Maillard reaction begins in earnest, the specific aromatic character of a searing burger emerges. The dozens of volatile compounds that the reaction generates, the combination of sweet and savory notes that the nose reads as cooking meat. This smell is not metmyoglobin. It is entirely separate chemistry happening on the surface at far higher temperatures. The two things, the browning smell and the browning color inside the meat, are produced by different reactions running simultaneously, which is perhaps why a burger that smells cooked can still be pink in the middle. The nose is tracking the surface. The color is tracking the interior. They are not the same report. I had never actually separated them in my mind before I read into this. They had always arrived together as a single signal, and I had treated them that way. The temperature sequence of a cooking burger is a story in 3 acts. Below 50 degrees, the iron holds. Between 60 and 70, the iron loses its electron. Fe3+ forms. The red disappears. Above 80, the protein surrounding the iron collapses and the finished state locks in. The chemistry does not reverse. The brown does not return to red when the burger cools. Once Fe3+ has formed, the iron is in its new state, and the conditions of a kitchen do not provide what would be needed to return it. So the cooking of a burger, red at the level of the iron atom, is a sequence of irreversible chemical steps driven by temperature and the availability of oxygen. Red to brown is Fe2+ to Fe3+, the loss of one electron, an oxidation, a rust. And it is exactly here, at this specific chemical fact, that the video's central parallel becomes possible to state fully. Because the same sequence, the same Fe2+ to Fe3+ electron transfer, happened across the surface of an entire planet. Not in 4 minutes, not in a kitchen, over billions of years, across hundreds of millions of square kilometers, driven by forces that have nothing to do with a pan or a flame. What was Mars before that transfer completed? What did the planet look like when the iron on its surface was still in the Fe2+ state? The answer is not what most people would picture when they hear the name of that planet. And that is the next chapter's question. It begins in a period before the red existed, before the dust, before the color that now makes Mars recognizable from Earth on a clear night. The Mars that most people carry in their minds is the one visible from Earth on a clear night, a point of reddish light in the sky, warm-colored and slightly distinct from the blue-white of stars. The Mars of photographs is the same image intensified. Orange dust plains, reddish rocky outcrops, a pale pinkish sky lit by a sun that from that distance appears smaller and colder than the one that lights this room. The color is so consistent and so defining that the red planet has become not just a description, but a name. 4 billion years ago, Mars was not red. The iron on its surface was still in the Fe2+ state, and most people hearing that assumed the planet must have looked broadly similar, just a different shade of the same general color. That assumption needs revising. Mars formed approximately 4.5 billion years ago, in the same period of accretion and collision that assembled the other rocky planets of the inner solar system. In the earliest period of Martian geological history, the Noachian period, which ran from roughly 4.1 to 3.7 billion years ago, Mars had liquid water on its surface, not as a curiosity or a trace. River valley networks carved across the terrain, ancient lake beds formed and persisted. The Mars Recollection Orbiter has mapped valley networks consistent only with long-duration flowing water, and sedimentary structures in Gale Crater confirm that bodies of standing water once occupied what is now dry rock. Some of these networks are thousands of kilometers long, branching like the drainage basins of terrestrial rivers. Mars was wet. The surface carried liquid water for an extended period, leaving a mineralogical record still legible today. The iron-bearing minerals on early Mars were predominantly silicates, specifically olivine and pyroxene. These are the minerals that form when iron-rich magma cools. Iron bonded into silicate crystal structures, the Fe2+ state locked into the mineral lattice. Olivine is green to yellowish green, common in the Earth's mantle, where it is the most abundant mineral by volume. Pyroxene is darker, gray to black-green. Both look nothing like the red iron oxides that now dominate the Martian surface. And both carry iron in the Fe2+ state, the unreacted state, the form the iron occupies before oxygen takes its electron. Most people carry a single image of Mars: orange dust, reddish outcrops, a landscape that has always looked that way. And for the surface visible today, that image is accurate. The rust red exists and is real. But beneath the surface layers, in the oldest exposed terrain, the mineral colors are gray-green and dark yellow-black, olivine and pyroxene, both carrying Fe2+ iron that has not yet lost its electron. The Mars beneath the visible Mars has not fully rusted. In places where the geology has buried those ancient silicates deeply enough, they sit chemically unchanged from the planet's formation. The orange visible from Earth is the record of what happened after. What was there before is still there underneath. It simply has not been seen yet. Perhaps you have looked at photographs of the oldest Martian terrain, the heavily cratered highlands, where the CRISM instrument has mapped exposed rock compositions. These photographs may appear orange at first glance. I too saw them as orange at first. But science notes that it is darker, closer, as it were, to gray-green. We can say that this is what iron-rich silicate rock looks like before the oxidation runs. We cannot deny that these photographs are a little different in color from the Mars we know, the Mars we recognize. This is what I find genuinely difficult to picture, and I want to say so plainly: Mars as a dark planet. The images are so thoroughly orange in the cultural memory that trying to imagine a Noachian Mars, a darker surface, olivine and pyroxene, where hematite and ferrihydrite now sit, liquid water moving across terrain that had not yet oxidized, requires something of an effort. But the mineralogy is clear. The Mars Reconnaissance Orbiter's CRISM instrument has detected olivine in exposed geological sections dating to the Noachian period, in terrain buried before the widespread oxidation of the surface began. That olivine was not subsequently altered. It was buried before the conditions for Fe2+ to Fe3+ conversion reached it. It is preserved as a record of what the surface looked like before the chemistry ran. An analogy that is imperfect but useful. If you sealed a piece of beef in a perfect vacuum the moment it was cut, and that seal was never broken, the myoglobin inside would remain in its deoxymyoglobin state. The Fe2+ iron in a purple-red form, never progressing toward the brown of metmyoglobin. The olivine and pyroxene in the buried Noachian terrain are something like that sealed piece of meat. The conditions for oxidation never arrived in the layers where they sit. They retained their Fe2+ state while the layers above them changed. The analogy breaks down at the scale and the mechanism, but the basic principle holds. Remove the conditions for oxidation, and the Fe2+ state persists. Because some things do not change, we assume that that thing does not change. But this shows not that the thing itself does not change, but that it was not in an environment that would force it to change, or that no event or chemical element that would have triggered that change ever occurred. There is a detail here that took me some time to fully absorb. The olivine in those buried Noachian sections is not just old, it is chemically unchanged across 4 billion years. Sitting underneath oxidized rock above it, in a layer where the conditions for electron transfer never materialized, it has stayed in its Fe2+ state since the planet was forming. The same oxidation state of the iron in raw beef at the back of a refrigerator, separated by 4 billion years and 400 million kilometers, but chemically equivalent. I am not entirely sure what to do with that, but I find it difficult to move past without noting it. What caused the oxidation to run in some layers and not others? Planetary scientists have not fully resolved. The mineralogy of the Noachian and post-Noachian terrain is reasonably well characterized, but the boundaries, precisely when a given region transitioned from Fe2+ silicates to Fe3+ oxides, what drove that transition in that location at that specific time, are not settled. Different regions show different mineralogical signatures, and the pace of oxidation varied in ways that current data do not completely explain. The dominant iron mineral on Mars today is hematite, Fe2O3, a fully oxidized iron oxide in which the iron is in the Fe3+ state. Hematite is the same compound that gives rust its orange tone. It covers extensive regions of the Martian surface, confirmed across decades of orbital and surface observation. The Mars Global Surveyor's Thermal Emission Spectrometer mapped hematite distribution across large areas of Meridiani Planum in the late 1990s. What that mapping revealed was the scale of the oxidation, not a patchy or localized process, but a planetary scale transformation from Fe2+ silicates to Fe3+ oxides, across a time frame and spatial extent with no equivalent in anything observable in a kitchen. Iron, when it oxidizes, behaves as if it has no interest in reversing what it has done, as if it settled into the Fe3+ state and found it sufficient. This quality is the same whether you are looking at the surface of a nail left in rain for 3 weeks or reading the mineralogical map of a planet. The direction does not change. The ending is always the same color. The moment that perhaps most sharpened the picture came in 2004. The Opportunity rover, operating in Meridiani Planum, found the surface littered with small spherical concretions, roughly the diameter of a pea, scattered across the rock's surface and loose on the ground. They were nicknamed blueberries for their shape, though the name is misleading. They are not blue and they are not soft. Analysis confirmed they were hematite, small, dense spheres of Fe3+ iron oxide that had formed by a process of groundwater percolation through the rock, the iron precipitating out as the chemistry of the water changed. They were not blown there, they grew there, in the rock, at a time when water was moving through the substrate, and they remained on the surface after the surrounding rock eroded away, leaving the hematite spheres sitting loose like something scattered by a hand. The hematite blueberries at Meridiani told scientists two things. First, liquid water had once moved through this terrain because the concretion process requires it. Second, the iron in that water had been oxidized to Fe3+, had lost its electron to oxygen in the same way the iron in a cooking burger does, though under conditions and across timescales almost impossible to hold in mind at the same time as a kitchen event. Each blueberry is a small chemical record, a sphere of iron that completed the same Fe2+ to Fe3+ transition the myoglobin in a burger completes in 4 minutes, but did so slowly in groundwater, in a rock, on a planet 400 million kilometers away. I am not sure there is a tidy way to absorb that. It simply sits there as a fact, and the fact is strange. Mars began with iron-rich silicate minerals, olivine, pyroxene, carrying the Fe2+ iron in their lattice structures. The surface was darker than what is seen today. Water flowed across it. The planet was wet and chemically active in ways that left sedimentary records still legible in the geology. Then something began to change. The liquid water retreated. The atmosphere thinned. The surface was exposed to different chemical conditions, and the Fe2+ iron in the minerals began to lose its electron. Fe3+ began to form. Hematite appeared where olivine had been. The surface reddened, not all at once, not uniformly, but progressively, region by region, layer by layer, across a timescale that requires a very different sense of duration than the 4 minutes it takes to cook a burger. What drove that process, and how long did it actually take? Those are the next questions, and they require going into the chemistry of Mars's atmosphere, the role of water in accelerating oxidation, and an honest account of the fact that planetary scientists do not all agree on what the primary oxidation pathway was. There are 3 competing hypotheses, and the evidence for each is real. The iron did not know it was coloring a planet. It simply did what iron does when oxygen and time are present. The burger does exactly the same thing on a Tuesday evening in 4 minutes. The scale is different. The chemistry is not. Mars did not rust the way a nail rusts. A nail left in damp air has everything it needs: oxygen dissolved in water, direct contact at the surface, an ambient temperature that allows the reaction to proceed without interruption. The conditions are present, simultaneous, and local. The rust that forms on a nail in a week would be visible to anyone watching. One day I was fixing a table in the yard, and it started to rain. As I was carrying the boards, hammer, and other tools back into the house, a nail fell and was left behind. The next morning, when I brought the tools back out to continue working on the table, I saw that nail on the grass. I picked up that nail. Because water had touched it, it had already begun to rust. When I touched the rust, it crumbled like grains of sand. It just shows that sometimes chemical processes can happen that quickly. What happened on Mars was different in almost every particular except the chemistry itself. And understanding how a planetary surface rusts, how billions of square kilometers of Fe2+ iron silicate become Fe3+ iron oxide over a timescale that exceeds the current age of complex life on Earth, requires going into the specific conditions of a planet that is now cold, thin-aired, and largely silent, and reconstructing what those conditions used to be. The geological period in which most of the surface oxidation is thought to have occurred is called the Hesperian, running from roughly 3.7 to about 3 billion years ago. This is the period that followed the Noachian, which was Mars at its wettest and most geologically active. The Hesperian is when the transition began in earnest. Mars was losing its surface water. Its magnetic field had already collapsed. The global magnetic field that once deflected solar wind disappeared, probably more than 4 billion years ago, for reasons that are still debated in the planetary science literature. Without that field, the solar wind began stripping hydrogen from water molecules in the upper atmosphere. Over geological time, the loss of hydrogen meant the loss of water, not all at once, but gradually, irreversibly, across millions of years. The surface dried, the atmosphere thinned. The landscape that had supported river valley networks and standing lakes became increasingly arid. And as the water retreated, the surface iron minerals were exposed to a different chemical environment than the one in which they had formed. The exact mechanism of what drove the Fe2+ to Fe3+ conversion across this drying surface is, and I want to be direct about this, not settled. There are 3 competing hypotheses among planetary scientists, each with genuine evidential support, and no single mechanism has been established as the dominant pathway. The first hypothesis is direct atmospheric oxidation, the same process as rusting on Earth, where molecular oxygen in the atmosphere reacts with iron at the surface. The difficulty is that Mars's current atmosphere is roughly 95% carbon dioxide. Molecular oxygen makes up less than 1% of the atmosphere today. Whether the early Martian atmosphere ever contained oxygen at concentrations sufficient to drive large-scale surface oxidation is constrained by the available evidence, and that evidence does not strongly support a high-oxygen early Mars. The hypothesis is possible. It is not well supported by current atmospheric models. The second is photochemical. Without its global magnetic field, the Martian surface receives ultraviolet radiation from the sun with very little shielding. Ultraviolet radiation drives chemical reactions that do not require molecular oxygen as the oxidizing agent. UV acting on the minerals and trace atmospheric compounds present at the surface can generate highly reactive oxidizing species, compounds capable of pulling electrons from Fe2+ iron without needing a reservoir of oxygen gas to draw from. The spatial distribution of certain Fe3+ minerals on Mars is consistent with this pathway, and the absence of a magnetic field for much of Martian geological history makes UV exposure a persistent and energetically significant factor. There is nothing particularly dramatic about ultraviolet light as an oxidizing force. It is the same radiation that slowly strips color from a car left in direct sun over several summers, working without obvious event, accumulating almost invisibly. On a planetary surface with no magnetic shield and very little atmosphere to absorb it, the cumulative effect over billions of years is a different order of consequence entirely. The third hypothesis centers on hydrogen peroxide. Ultraviolet radiation acting on water vapor in the thin Martian atmosphere produces hydrogen peroxide, H2O2. Hydrogen peroxide is a powerful oxidizing agent. Formed in the atmosphere, it can deposit onto the surface and react with Fe2+ iron minerals, converting them to Fe3+ oxides, while oxidizing other surface compounds. The Viking landers detected something in 1976 that fits this picture. When they added water to Martian soil samples, the soil reacted vigorously, releasing oxygen in a way that is most consistent with the presence of a strong oxidizing compound in the surface material. Hydrogen peroxide, formed by UV photochemistry, is the explanation that fits the Viking data most naturally, though it has not been confirmed directly. What the Viking result established clearly is that the Martian surface is chemically reactive in a way that a purely inert iron oxide dust would not be. Something oxidizing is present in that soil. What exactly it is and where it came from is part of the same unresolved picture. The most honest summary of where the science stands is this. All three mechanisms likely contributed in proportions that varied by location, depth, and geological period. The surface oxidation of Mars was not driven by a single clean process. It was the accumulated result of multiple overlapping chemical pathways operating across billions of years and varying conditions. Scientists continue to map the mineral evidence that each pathway leaves behind, using orbital spectroscopy and surface analysis, trying to separate what each mechanism produced in each region. The work is ongoing. The full answer is not yet in. What the Curiosity rover detected in 2018 adds a genuinely puzzling layer to this picture. Its instruments found that molecular oxygen in the thin Martian atmosphere fluctuates seasonally, rising in spring and summer, falling in autumn and winter, at rates that current models of Martian atmospheric chemistry cannot explain. You might expect such a fluctuation to resolve quickly once the instruments were calibrated and the models refined. It has not resolved. The oxygen is appearing from somewhere. It is disappearing somewhere. No known process operating on Mars today fully accounts for the variation. This is not a modeling uncertainty or a gap in the instruments. It is a real, measured observation sitting in the data with no accepted explanation beside it, and what it means for understanding the ongoing chemistry of the Martian surface, and by extension, the history of its oxidation, remains genuinely open. Mars does not behave like a planet whose chemistry has finished. It continues to show its work in ways that science has not yet fully read. I have a personal note to add here, and it is not a dramatic one. When I was reading through the material for this chapter, I kept returning to the phrase active research question, the way it appears in the literature when scientists are describing something they genuinely do not yet understand. It appears around Mars's oxidation mechanism with a frequency that initially surprised me. I had assumed this was settled. It is not. And the more I read about what the orbital instruments have found, the patchwork of different Fe3+ minerals in different regions, the seasonal oxygen fluctuations, the boundaries in the geological stratigraphy between phyllosilicates and oxides, the clearer it became that Mars is still revealing the details of its own chemical history. The record is real. The reading of it is still incomplete. What makes the three hypothesis problem genuinely interesting, rather than simply unresolved, is that each pathway leaves a different chemical signature in the minerals it produces. Atmospheric oxidation, driven by molecular oxygen, tends to produce well-ordered hematite. UV photochemical pathways and hydrogen peroxide reactions tend to produce more disordered iron oxides, including ferrihydrite. Mapping which compounds appear where and at what depth in the geological sequence is one of the ways scientists attempt to separate the contributions of each pathway after the fact. The mineral distribution is not just the record of the oxidation. It is potentially the evidence that distinguishes between the mechanisms that produced it. There is something physical about the end state of this process that is worth describing plainly. The reddish color that makes Mars identifiable from Earth on a clear night, and that colors every photograph taken from the surface, is produced primarily by a layer of fine dust. That dust is predominantly ferrihydrite, a form of iron oxide that formed at low temperatures in the presence of water and never fully committed to a more stable crystalline structure. And it circulates through the Martian atmosphere in dust storms that can, at their largest, cover the entire planet simultaneously. The 2018 global dust storm, which lasted for months and reduced surface light levels by approximately 90% in some locations, was a ferrihydrite suspension, a planet-wide cloud of oxidized iron particles fine enough to stay airborne for weeks. But the dust itself, for all its visual impact, is not thick. In many regions, the reddish layer is only millimeters deep. Beneath it, the surface is considerably darker. The planet is red at its skin. Underneath that skin, the geology is older, darker, and in places chemically closer to what was present before the Fe2+ to Fe3+ conversion ran. The 2018 global dust storm had one consequence that deserves to be stated directly. Opportunity, the rover that had found the hematite blueberries at Meridiani Planum, that confirmed goethite at the same location and established the presence of ancient liquid water there, was running on solar power. It had been operating for nearly 15 years at that point, well beyond its original 90-day mission specification. When the 2018 global dust storm reduced incoming sunlight to levels insufficient to charge the rover's batteries, Opportunity went into a low-power fault state. NASA made over 1,000 recovery attempts across 8 months. The final transmission attempt was in February 2019. There was no response. The rover that spent years reading the iron record of Mars went silent under a cloud of the same ferrihydrite dust it had spent years helping to characterize. The oxidized iron particles that the storm carried across the planet blocked the sunlight that powered the instruments studying them. There is nothing dramatic to make of that. It is simply the physical environment operating as it does, without regard for what is in it. The nail on a windowsill comparison, which this chapter opened with, is imperfect in ways worth naming. A nail is a steel alloy sitting in damp air. Mars was an iron silicate mineral surface in a thinning atmosphere driven by UV radiation and lacking a magnetic field. The chemistry of the electron transfer is the same. The conditions surrounding it are not comparable. The comparison earns the direction of the reaction. It does not describe the mechanism, and it would be wrong to read it as implying more than that. Iron, across this story, behaves as something that holds its original state until the conditions to change it are met, and then commits to the new state permanently. The Fe2+ silicates of Noachian Mars persisted for hundreds of millions of years while the chemistry of the planet remained in the right configuration to preserve them. When the conditions changed, when the water retreated, when the UV flux increased, when the oxidizing chemistry became available, the conversion ran, and what it produced does not revert. The Fe3+ iron oxides that now color the surface are the record of a set of conditions that no longer exist. The conditions changed, the chemistry ran, the iron stayed where the chemistry put it. A burger patty oxidizes in 4 minutes, while Mars needs billions of years to complete this process. Here, the chemistry remains the same, but the conditions are completely different. This is nothing unusual. It is simply a proportion. The time scale between a cooking burger and a rusting planet is not simply large. It is a number. And the number, when calculated, is this. 4 billion years contains approximately 500 trillion 4-minute intervals. To put that another way, if you cooked a burger from start to finish, placed it aside, immediately started a new one, and continued that process without interruption every 4 minutes for as long as it has taken Mars to oxidize its surface, you would have cooked 500 trillion burgers. The stack of those patties, laid flat, would extend further than the distance from Earth to the Sun, 30 times over. The natural assumption, looking at a ratio this large, is that the two processes must be fundamentally different. 500 trillion to 1 does not look like the same thing running at different speeds. It looks like two entirely different phenomena that happen to share a color. That assumption is what this chapter exists to correct. The chemistry is identical. The conditions that drive it are not. And conditions in chemistry determine rate, not direction. The same principle, encountering different amounts of available energy, produces different speeds. This is not a special case or a quirk of iron chemistry. It is how chemical reactions behave in general. The stack image is a useful illustration and not much more. The point is not the stack of patties, which is an absurd object, but what the number requires to become imaginable at all. 500 trillion needs physical staging before it carries any weight. The stack provides that staging. What the staging does not provide is any real sense of the scale itself. That simply does not fit inside an image. In the burger, The electron transfer is driven by heat. The cooking surface delivers approximately 180 to 200 degrees Celsius to the patty, a representative range for a domestic pan, though the actual figure varies with the pan material and how long it was preheated. At that temperature, every molecule in the system is moving with enormous kinetic energy, colliding more often, more forcefully, exchanging electrons faster. The myoglobin's heme group, surrounded by a warm protein environment saturated with oxygen from the surrounding tissue, completes its Fe2+ to Fe3+ conversion rapidly because the energy is high, sustained, and applied directly. 4 minutes from pink to brown is the result of conditions engineered to produce exactly that outcome. High temperature, direct oxygen contact, a protein environment that facilitates the transfer. On Mars, the average surface temperature is approximately -60 degrees Celsius, a planetary mean that conceals a significant range from near zero at the equatorial surface in summer to below 120 at the poles. The chemistry of oxidation varied accordingly across the surface, and no single temperature figure describes what the reaction encountered. At any point within that range, the kinetic energy available to any chemical system is a fraction of what a kitchen pan provides. Reactions that complete in minutes at 180 degrees may require years at -60. Scale years to billions of years across a planetary surface that is simultaneously losing its water, thinning its atmosphere, and changing its chemical environment in ways that proceeded over geological time, and the slow accretive pace of the Fe2+ to Fe3+ conversion becomes physically coherent. The chemistry was not slower because it was different. It was slower because the energy to drive it was available only in small amounts, intermittently, from UV radiation and limited atmospheric chemistry, rather than from a sustained heat source at hundreds of degrees. Suppose you had a piece of iron in a sealed room with oxygen at -100 degrees. The iron would, in principle, oxidize. Fe2+ would move toward Fe3+. The same electrochemical principles apply. But the rate would be so slow as to be nearly undetectable across a human lifetime. Change the temperature to 500 degrees, and the same piece of iron oxidizes visibly in minutes. The principle has not changed. The rate has changed by many orders of magnitude. Temperature is not a modifier of the chemistry. It is a governor of how quickly the chemistry's direction is expressed. The iron atom, in the deepest sense, does not register the difference. When conditions permit the electron transfer, when an oxygen molecule with sufficient energy makes contact with the Fe2+ iron in a configuration that allows the exchange, the transfer occurs. Whether that moment comes after 4 minutes of cooking or after billions of years of slow planetary chemistry does not change what happens at the moment of transfer. The electron leaves. Oxygen takes it. The iron is Fe3+. The chemistry follows the same electrochemical rules regardless of the duration that preceded the moment of transfer. What the rate difference explanation leaves out is something that shifts the scale of the picture further, and it is worth going into. The Fe2+ to Fe3+ conversion is not something unusual or exotic. It is one of the most common chemical reactions operating in the natural world, and it appears in contexts far beyond burgers and Mars. The orange rust on an old metal gate is the same reaction. The reddish-brown staining on cliff faces where iron-bearing rock has been exposed to weathering, the same reaction, running at the pace of geological erosion. The reddish color of certain soils, the deep red Mediterranean soils known as terra rosa, and the similarly red tropical soils formed under centuries of intense weathering, produced by the same Fe2+ to Fe3+ conversion, in some cases running for millions of years at low temperatures and producing hematite in the upper soil layer. Even the reddish tones in certain sandstone formations, the kinds found in desert canyon country, are hematite produced by ancient groundwater interactions with iron-bearing minerals in the rock. Iron is the most abundant element on Earth by mass, comprising roughly 1/3 of the planet's total mass, concentrated in the core and distributed through the crust and mantle. The Fe2+ to Fe3+ electron transfer operates on iron wherever iron and oxygen coexist under conditions that permit the exchange. This means it is running right now, at this moment, on every exposed iron surface in oxidizing conditions anywhere on Earth. The surface of every iron-bearing rock face exposed to air and moisture, every corroding steel structure in a coastal environment, every piece of iron left outdoors after rain. Once I pulled a nail out of an old piece of wood. Who knows how much rain that wood had been exposed to over the years? The tip of the nail had properly rusted. The middle was orange, but the head still held on to that metallic color. Meaning, on a single piece of metal, there were 3 chemical states. What those color states represent, a gradient of Fe2+ to Fe3+ along a single small object, produced by differences in oxygen and water exposure over the same duration, makes it a different object than it was before the reading. The orange tip completed its electron transfer years ago. The silver head has not yet. The 2 colors on one nail are the same story as the 2 colors on a cooking burger and the surface of Mars. The same principle at 3 scales on a single piece of metal the length of a finger. The iron in the beef of the burger did not begin in the animal. It arrived through the food chain, taken up from iron-bearing minerals in the soil by plants, metabolized through the food chain into the muscle tissue of the animal, incorporated into the myoglobin protein that held it in the Fe2+ state throughout the animal's life. The iron in that heme group may have spent time as a component of a soil mineral before it spent time inside a living organism. It may have been in Fe3+ form in the soil and been reduced back to Fe2+ during biological uptake. It has a history that long precedes the burger, and that history involves the same electron it transfers when the cooking is done. That chain is worth holding for a moment, not as a philosophical point, but as a physical one. The iron that makes a piece of beef red was not manufactured by the animal. It was taken up from the ground. Before it was in myoglobin, it was in a mineral. Before it was in that mineral, it was somewhere else. The Fe2+ state of the iron in a raw piece of meat is not the iron's natural default. It is a state that biological chemistry worked to maintain, reducing Fe3+ back toward Fe2+ to make the iron useful for oxygen storage. The burger's iron arrived at the heme group through a chain of chemistry that ran in the opposite direction from the one that will complete in the pan. Reduction first, oxidation at the end. The reaction the cooking completes is, in this sense, a return, not a beginning. There is a deeper record in the Fe3+ minerals on Mars, and it is the subject of the next chapter. Because the different Fe3+ minerals that different conditions produce, hematite under dry, high-temperature oxidation, goethite in the presence of liquid water, ferrihydrite under cold aqueous conditions, are not simply different names for the same end state. They are chemical signatures of the conditions that produced them. Reading which Fe3+ mineral is present in which location on Mars is reading a record of the conditions that drove the oxidation there. The iron committed to the state the conditions made possible, and the specific compound it committed to carries information about those conditions permanently. The mineral distribution across Mars is, in a precise sense, a map of a chemical event that lasted billions of years, and the instruments reading it are doing something that has no equivalent in the kitchen. They are reconstructing the conditions of an ancient planetary environment from the compounds the iron chose under those conditions to become. A rock is not simply a rock to someone who has learned to read mineralogy. What a geologist sees in an exposed cliff face, in a road cut, in the sedimentary layers of an ancient basin, is a record of the conditions that produced each layer, the temperature, the pressure, the chemistry of the fluids that were present, the duration over which each compound had time to crystallize into its final form. None of this was written down. None of it was observed when it happened. It is encoded in the mineral itself, in its crystal structure, its chemical formula, its associated minerals, the texture of the grain. The rock is its own record. The Fe3+ iron oxide minerals on Mars are a geological record of this kind, and what makes them extraordinarily informative is that the three main Fe3+ minerals found on the Martian surface do not form under the same conditions. They form under substantially different temperatures, different water chemistries, and different rates of reaction. Reading which mineral is present in which location and at what depth within the geological sequence is reading the specific conditions of Mars at the time and in the place where that mineral crystallized. The iron committed to a specific Fe3+ compound determined by what surrounded it when the oxidation ran. The compound preserves that information permanently. The most committed form of oxidized iron, the one that forms when the process has run fully under dry conditions, with enough energy to order itself into a tight crystalline structure, is called hematite. Its chemical formula is Fe2O3, 2 iron atoms, 3 oxygen atoms, no water anywhere in the formula and none in the crystal structure. Hematite is what the iron becomes when the process has fully run. where hematite dominates on Mars, the geological interpretation is that oxidation occurred in conditions where liquid water was not abundant, or where the conditions were energetic enough and the process had run long enough that more water-bearing intermediate minerals had transformed into the dry, stable hematite end state. It is hard, a 5.5 to 6.5 on the Mohs scale. It is dense. The crystals in their most developed form have a dark, almost metallic luster, the kind associated with specular hematite, which ancient societies used as a mirror surface and a pigment simultaneously. The powdered form produces a reddish-brown streak, the iron oxide coloring that produces Mars's overall surface tone. Where hematite dominates on Mars, the geological interpretation is that oxidation occurred in conditions where liquid water was not abundant, or where the conditions were energetic enough and the process had run long enough that more water-bearing intermediate minerals had transformed into the dry, stable hematite end state. It is the signature of a completed oxidation under relatively dry chemistry. It is what the iron becomes when the process has fully run. Think of goethite as the mineral that formed with water still in the room, not as a companion to the reaction, but as a participant in it. That relationship is written directly into its chemistry, FeOOH. The OH at the end of that formula is a hydroxyl group, a unit of one oxygen atom bonded to one hydrogen atom, chemically bonded into the crystal structure itself. Water is not simply nearby when goethite forms, it is inside it, incorporated at the molecular level. When conditions change and the water eventually disappears, the goethite remains, carrying the chemical signature of the water that was there when it crystallized. The Opportunity rover confirmed goethite at Meridiani Planum using its Mossbauer spectrometer, an instrument that reads iron-bearing minerals by sending a precise beam of gamma radiation into the sample and measuring how the iron atoms inside it respond. The detection was not ambiguous, and its scientific significance was immediate. Goethite at that location meant liquid water had been present there at some point in Martian geological history when the goethite was forming. Now, goethite is not a stable end state. Under sufficient heat and dryness, it converts to hematite over time. That transformation is well documented. Given that Meridiani Planum has been exposed to billions of years of Martian conditions, you might expect the goethite to have long since completed that transformation. That it has not is itself informative. The goethite at Meridiani did not convert to hematite, not because something prevented it, but because the conditions that drive that conversion, sustained heat and prolonged dryness at sufficient temperature, were never present in that specific location long enough to complete it. The mineral stayed as goethite, and in staying, it preserved a chemical record that hematite could not have carried. The fact that the transformation did not occur is as informative as the mineral itself. Once, my friend introduced me to his friend, and from the collection he kept, I looked at a goethite specimen, one of his soil samples, and took the stone in my hand. It was heavier than its size suggested. On the freshly broken surface, a warm ochre-yellow color. On the weathered exterior, a slightly darker, richer orange-brown. There was a faint smell to it, too. The smell gave off a vibe like damp clay or the underside of a stone that had been sitting on wet ground for a while. That earthy quality, I learned later, is characteristic of goethite and related hydrated minerals. It is a piece of chemistry that carries something forward. There is something in the way a mineral preserves its formation conditions that deserves a moment of plain attention. Not a conscious one. A crystal does not experience the environment that produced it, and it does not remember anything. But it holds the structure that those conditions made possible, and that structure can be read back out by the right instrument. Goethite's OH groups are there because water was there. There is no water in hematite's formula because there was no water there either. The mineral, of course, does not choose this of its own will. Because the conditions are this way, the mineral conforms to those conditions. Ferrihydrite completes the set, and it does so as what I would call a first draft mineral. Not the final form iron commits to, but the form it commits to immediately when the conditions for oxidation arrive too quickly or too cold for a more ordered crystal structure to assemble itself. Scientists call it a metastable precursor, the compound that forms first in many wet oxidation scenarios, which may then transform to goethite or hematite over time as conditions allow. Its approximate formula is Fe5HO8.4H2O, though even this is an approximation, and the exact composition of natural ferrihydrite is still a subject of research. Ferrihydrite is provisional in a way that hematite is not. It formed fast, under conditions that did not give the iron time to settle into something more stable, and it has been waiting, in a chemical sense, for the conditions that would allow a more committed structure to form. Its presence in the Martian dust is significant precisely because ferrihydrite is not a stable end state. It should, under conditions allowing sufficient energy and time, transform into hematite or goethite. Where it persists on Mars, in the fine reddish dust that blankets the surface and fills the atmosphere, the interpretation is that it formed under conditions too cold or too brief for the more stable minerals to crystallize fully, and that those conditions then changed in a way that preserved the ferrihydrite rather than allowing it to transform. The dust is carrying a chemical signature of cold, rapid, wet oxidation, and then effectively frozen in that intermediate form by conditions that changed before the transformation to a more stable phase could complete. What this means in practical terms is that the Martian dust tells a different chemical story than the hematite in the rock beneath it. The dust says cold, fast, wet, incomplete. The hematite says dry, slow, and fully committed. The same planet carries both records simultaneously, one in its finest particles suspended in the atmosphere, one in the rock beneath the surface. They do not contradict each other. They record different episodes in different places of the same long conversion. The orbital instrument that has mapped these mineral distributions most comprehensively is the CRISM spectrometer aboard the Mars Reconnaissance Orbiter. CRISM measures infrared and near-infrared light reflected from the Martian surface in 544 different wavelength channels simultaneously. Different minerals have distinctive spectral fingerprints, characteristic patterns of absorption and reflection at specific wavelengths that allow identification from orbit at a spatial resolution of approximately 18 meters per pixel. The maps it has produced are spectral measurements verified against laboratory analysis of the same minerals on Earth, translated into mineral identifications across the planetary surface. What those maps reveal is that Fe3+ mineral distributions on Mars are not uniform and not random. Hematite, goethite, and ferrihydrite cluster in different regions and appear at different depths within the geological sequence. The spatial pattern is not the result of random deposition. It is the record of a spatially varied oxidation process. Different conditions producing different minerals in different locations across a timescale that no single process drove uniformly. The most informative boundary in this record, the one that carries the most direct information about the sequence of events on Mars, is the contact between phyllosilicates and Fe3+ oxides in the geological stratigraphy. Phyllosilicates are clay minerals, many of which contain Fe2+ iron, and they form when liquid water interacts with silicate minerals over extended periods under relatively neutral or mildly alkaline conditions. They are found in the oldest exposed Martian terrain, the Noachian surfaces, the layers that were laid down during the wet, geologically active early period of Martian history. Above them in the stratigraphic sequence, in younger layers, Fe3+ oxides dominate. The transition from phyllosilicates to Fe3+ oxides is not simply a change in mineral type. It is a chemical timestamp, the record of when, in that specific location, the conditions shifted from those that produce Fe2+ clay minerals to those that drive Fe2+ to Fe3+ conversion and produce iron oxides. Reading that boundary in the rock is reading the moment Mars changed. Not across the whole planet simultaneously. The boundary appears at different depths and different ages in different locations, consistent with a spatially and temporally complex transition rather than a single global event. But where it is exposed, where erosion has cut through the stratigraphy and brought it to the surface, it is a legible chemical record. Phyllosilicates below, wet conditions, Fe2+ iron preserved. Iron oxides above, drier or more oxidizing conditions, Fe3+ formed. The line between them is the line between two states of a planet. What is less settled, and what remains an active area of planetary science research, is the precise sequence and timing of when different regions underwent their transitions and what drove the regional differences in mineralogy. Why does one region preserve goethite while a neighboring region shows only hematite? Is that a difference in water availability, in temperature, in the duration of the oxidation, in the specific pathway that drove it? The data is available. The interpretation is ongoing. Scientists have the map. They are still working out the full history it encodes. The iron did not choose what compound to become. It became what the conditions made possible. and the conditions on Mars, varying by location, by depth, by geological period, produced a mineralogical record that is still being read. The planet's Fe3+ iron minerals are its own account of what it went through, not written in language, written in chemistry, in a compound structure that formed once under specific conditions and has preserved the record of those conditions ever since. The iron atom in the myoglobin heme group has no awareness of the reaction it is undergoing, no sense of the 4 billion years over which the same reaction reshaped a planet, no relationship to the Fe3+ iron oxides mapped from 300 kilometers above a cold, dry surface. The electron simply leaves. Oxygen takes it. The iron is Fe3+. The color changes. The chemistry follows the conditions it finds itself in, without commentary, without reference to any other instance of the same principle operating anywhere in the universe. And yet, the conditions in a kitchen, a pan at 180 degrees, a piece of ground beef in direct contact with the metal, oxygen available from the surrounding air and dissolved in the tissue, are sufficient to drive the same electron transfer that required a planet and several billion years to complete at Martian ambient temperatures. The energy in the kitchen is so much higher than the energy on Mars that the same principle runs in 4 minutes that ran over billions of years elsewhere. This is not a curious coincidence. It is a consequence of what temperature does to the rate of a fixed chemical law. What those Fe3+ minerals on Mars physically are, as objects, not as abstractions, is worth holding for a moment before moving to the principle they illustrate. I have held this stone before. It is heavier than it appears. That weight announces itself before the hand has fully closed around it. The surface catches the light in a way that reads almost exactly as metal, but draw it across an unglazed tile and the metallic impression disappears entirely. In its place, it leaves a warm iron-red streak. That streak color, that specific dusty iron red, is what colors the Martian surface from a distance of hundreds of millions of kilometers. The same compound, the same color, one in my hand, one on a planet I will never visit. The Fe3+ minerals on Mars, the hematite spheres at Meridiani Planum, the goethite that records water moving through an ancient terrain, the ferrihydrite in the thin reddish dust that planetary storms have been lifting and carrying for longer than complex life has existed on Earth, each formed under conditions that no longer exist. The conditions changed, the compounds remained. And what they are now, stable and chemically committed, carrying in their crystal structures a permanent record of the moment and manner of their formation, is the physical meaning of material continuity. The chemistry does not need to be ongoing. The record is already made. There is a version of this observation that could be made to sound dramatic, that the ordinary and the planetary are secretly the same, that the mundane hides something vast, that every kitchen is a microcosm of geological history. That version adds something the chemistry itself does not contain. The chemistry contains a simpler and, I think, more durable observation. The same electrochemical principle operates at every scale at which iron and oxygen coexist under conditions that permit the exchange. The kitchen and the planet are two of countless instances of that principle in operation. They follow the same law openly in plain sight, and have done so since there has been iron and oxygen in the universe. The iron atom in the myoglobin heme group follows the same electrochemical rules today that it followed when the first Fe2+ iron silicates on Mars began losing their electrons to whatever oxidizing conditions were available 3.5 billion years ago. Those rules have not changed because they cannot change. They are, in a sense, a description of what electron transfer between iron and oxygen is, not a rule imposed on it from outside. The conditions that drive the reaction vary enormously. The reaction itself does not vary at all. A question worth asking plainly and then answering without ceremony. What does it mean for a chemical principle to be invariant across this range of scales and conditions? Not philosophically, physically. It means that wherever iron in the Fe2+ state encounters sufficient oxidizing conditions, the electron will leave and the iron will become Fe3+. The timescale will be determined by the energy available. The direction will not be negotiable. This is, in a measurable sense, one of the oldest consistently operating chemical processes that can be observed directly. The rusting of iron, the movement of Fe2+ toward Fe3+ in the presence of an oxidizing agent, predates the oxygen-rich atmosphere of Earth. The Great Oxidation Event, approximately 2.4 billion years ago, transformed Earth's atmosphere from a reducing environment to an oxidizing one, driven by biological photosynthesis. Before that event, iron was oxidizing through different electron acceptors, sulfate, nitrate, and, in some geological environments, reactions driven by early forms of microbial chemistry that extracted electrons from iron as part of their metabolism. To be honest about what I mean by different electron acceptors, there is no analogy from the modern kitchen that captures what reducing atmosphere chemistry actually looked like. The analogy breaks before it starts, which is why I have not tried to provide one. What can be said is that the direction of the transfer was the same. The agent driving it was not oxygen. The outcome, Fe2+ moving toward Fe3+, was. The evidence for all of this is considerably thinner than the evidence for what we can observe today. Pre-oxygen Earth chemistry is reconstructed from isotope records, trace mineral signatures, and microfossil data, not from direct measurement. The broad picture is well supported. The specific mechanisms and their relative proportions in different environments are still being refined. I am working from a scientific consensus, not from certainty. What is certain is that when oxygen became the dominant oxidant in Earth's atmosphere, the same principle continued, simply with a new, more abundant electron acceptor driving it faster. The chemistry did not change. The agent driving it changed. The iron's behavior did not. What I find myself left with after all the reading is not a clever connection, but a physical fact. The same electron, the same direction, the same compounds formed. Science did not make this strange, it made it specific. A report on a Mars rover detecting hematite now reads differently than it did before. A burger in a pan now reads differently. not because the science has changed, but because the connection between them. From the outside, it looked like a rhetorical choice. From the inside, it turned out to be a description of something that was already there. If one of these details stays with you, the specific mineral that records a wet environment, the 500 trillion to 1 ratio of timescales, the fact that the iron atom operates by the same rules regardless of whether it is inside a protein or embedded in a planetary surface, it may be worth leaving in the comments. The quietest observations from this kind of examination tend to be the most interesting ones, and some of them are observations that did not occur to me while writing it. There is something this video did not cover, and I want to name it. The browning of a burger's surface is not solely methioglobin. The crust that forms on a seared patty, the specific color, the aromatic compounds, the hundreds of distinct volatile molecules that produce what the nose reads as cooking meat, is produced by a different reaction, running simultaneously with the iron's oxidation, but at higher surface temperatures and through entirely different chemistry. What happens above 120 degrees at the surface of that patty, the specific chemistry between amino acids and reducing sugars, the cascade of intermediate compounds, the volatile molecules that make a kitchen smell the way a kitchen smells when something is cooking, is a story with its own depth and its own surprising connections. The compounds it generates number in the hundreds. Some of them appear in coffee. Some appear in the crust of bread. Some appear in chocolate. The same reaction that browns a burger's surface is the same reaction that produces the color and much of the flavor of roasted coffee beans and toasted bread. What the iron did connects a kitchen to a planet. What the surface chemistry does connects a burger to breakfast. And that story, if it were given the same attention that the iron received in this video, would take at least as long to tell properly. The iron in the myoglobin has now run its reaction. The burger is done. The Fe3+ is stable and will remain so. And somewhere else, on an exposed cliff face, on the surface of an old gate, in the thin reddish dust of a global Martian storm, the same electron is leaving the same iron under different conditions at a different rate for a different duration. The chemistry does not know the difference. Iron has throughout all of this simply followed its own principle without exception, regardless of the environment it has found itself in. It was doing this before anyone was watching, and it will continue doing its work long after the watching has stopped. Good night. See you in next video.